Today we're going to study the LC oscillator. So I'll put here LC or LC oscillation. So this L stands for inductor and C for capacitor. So we have a capacitor C and then we have an inductor L. Okay? Now, what happened, the current actually will go between L and C. The capacitor will have the current, will throw it back to the inductor. The inductor will get that current, will throw it back to the capacitor. So you have sometimes, you can have energy stored in the capacitor and energy stored in the inductor. Some of it, the total energy in the system, some of it will be stored in L, some of it will be stored in C. When the current, when this one is charged, at certain point, you can have all of the energy here and no energy here. And the total energy will be here. Sometimes the total energy will be there. So what happens is you have this back and forth energy transfer. So what we do this. We say the energy, total energy of the system is equal to UC, this is the energy stored in the capacitor, plus the energy stored in the inductor. The energy stored in the capacitor, we know, we studied it a while ago, before actually the corona break. And UL is the energy of the inductor, which we just studied like one video. You can find it in one video or two videos back. This is the energy stored in the inductor. This is the energy stored in the capacitor. So we take these two energies and we put them here. So I put U is equal to Q squared over 2C plus 1/2, let me go up here, I'm sorry, 1/2 Li squared. This is the energy stored in the system. This energy is constant. I put here constant. We assume we don't have any energy loss, so the energy is constant. Okay? Like a perfect oscillator, we don't lose any energy. It's like you have, for example, a perfect pendulum. Okay, it oscillates back and forth. So you don't have any energy loss. So the clock just keeps going back and forth, the pendulum non-stop. But you have energy loss due to air friction, due to the pivot point here. So you're going to lose energy. Same thing here. The current will go through the wire, going to lose energy due to heat. But we assume this energy is fixed, this energy. So if it's fixed, if we take derivative of it with respect to time, the derivative should be 0. So let's do that. So we put here du over dt is equal to 2q dot over 2c. You take 2 and q, and then you have to take derivative of q with respect to time. It just gives you q dot. So q dot is just a notation for dq over dt. So instead of putting dq over dt, I just put q dot. It's easy to put a dot instead of writing d over dt. Plus 1/2 Li, and then I put di over dt. And this is equal to 0. So this is going to give me, cancel 2, cancel. I have to put here 2, because when I take derivative, 2 is going to come out. So I have 2 Li di over dt. So I have 2 here at the top. Cancel these 2. So I will have q dot over c is equal to minus Li di over dt. Cancel. You see q dot? Remember, q dot is I. This is I. So I just cancel this, cancel that. And then I have Q over C is equal to minus L di over dt. This gives me Q over C is equal to minus L second derivative of Q over dt squared. So this will give me d squared of Q dt squared is equal to minus Q over LC. So look at this is a differential equation. Is differential equation. So first we need to know what we're looking for. What actually we're looking for is the frequency of oscillation. We're looking for F or omega. We're looking for omega. We know that omega is equal to 2 pi F. So if we know omega, we will know F. So we can find omega and then we find F afterwards. So we're looking for omega. So what we do, this is a second order differential equation. Do we know the trial solution will look like this? Q0, I put here sine omega t. You see, whenever you have some equation that looks like this, x is equal to some constant, and x you have x double dot, and then you have some equation that looks like this, its solution is going to be, this is an oscillation. When you see a differential equation looks like this, that's an oscillation. A solution will look like this. X is equal to x0 sine omega t or cosine omega t. So that's why you can see this and this to look the same. You have constant, I have the constant is 1 over LC, and then you have this Q variable, and then you have second derivative of the variable. So let's move this up and take Q, put Q dot is equal Q0 omega cosine omega t. And then I will take another derivative because I have a second derivative here. I put here Q double dot, which is actually dq over dt squared is equal, I put minus Q0 omega squared, and I put cosine omega t, sine omega t, I'm sorry, sine omega t. Okay, because the derivative of the cosine is minus sine. That's why I have that minus here. Now, look at this is Q double dot is this one. And Q is this one. So, I take this Q and put it there. And I take this Q double dot, which is this. And then I put it there. So I get minus Q0 omega squared sine omega t is equal to minus 1 over LC. And then I have to put Q. Q0 sine omega t. Look at this. Q0 cancels. Minus cancels. And then this sine omega t can cancel. We can say sine omega t is different from 0. If sine omega t is equal to 0, you're going to have 0 times anything is equal to anything times 0. So you just choose the case sine omega t is different from 0, cancel it. So omega is equal to 1 over square root of LC. But remember, omega is equal to 2 pi f. So I put here 2 pi f is equal to 1 over square root of LC. So here we get the frequency. 1 over 2 pi, 1 over square root of LC. This is the frequency of oscillation in the oscillator. Let me put here again capacitor, inductor. So they throw in the current back and forth at each other. It's going back and forth. So the period of oscillation, or the period for one cycle, is equal to 2 pi square root of L times C. Why? Because the period is equal to 1 over the frequency. And if you flip this, you get that. So now, this can be, you can make a clock out of this. How? You can choose an inductor or capacitor such that it give you 1 second. And then you have 1 oscillation per second. It's like a pendulum. You know, for a pendulum, what do we know? T is equal to 2 pi square root of L. This is the length over G. You can choose an L. G we know is 9.8. You can choose an L to give you T equal to 1 second. And then you can make an oscillation that goes back for 1 cycle is 1 second. Same thing here. You can choose certain L and certain C to give you 1 second. And then you can make a clock out of this. So, for example, the microprocessor in the computer needs a clock or a timer. There is an old timer that I studied a while ago. And this timer is called 55. It's like a chip. I used to work with it. This is a long time ago. It's called 555. You know? I don't know if they still use this timer now. But this timer is needed for the microprocessor, for the computer, to kind of keep track of the circuitry. Because you need to have a timer to keep track. If you send some signal, you will need to know what time it's sent, so the other one will receive it. This is important for circuitry. So I'm assuming, I think that this inductor capacitor, this kind of oscillator, is inside there. You know, inside this. I'm assuming, I don't know. I didn't open this chip. This is a chip. I didn't open it to see what's inside, but I'm assuming they use this kind of physics for a timer like this one. So this LC oscillator is really useful in electronics, useful in circuitry, useful in electrical engineering. Now, you see, I said that they share the energy. If you look at the spring, you have here, this is the mass, this is the spring. The energy in the spring is equal to the potential energy of the spring, which is half kx squared, and then you have the kinetic energy of the mass. So when this mass is moving with velocity through this origin, you have maximum kinetic energy, so I put here max. At this location, this mass has maximum kinetic energy and it's moving through the center. When it gets here, it will stop. And here you have velocity equal to 0, but then you have maximum x, maximum amplitude. So you get maximum potential energy. So the potential energy, 1/2 kx squared. So when the mass is here, you have the potential energy. When the mass is here, you have the kinetic energy. So you have this, the potential energy of the spring and the kinetic energy of the mass. So they share in the energy. So the mass gives its kinetic energy to the spring gets stretched or gets squeezed and change it to potential and give its potential energy to the mass. It's the same thing here with LC oscillator. This one gets the energy, and then the energy is stored in the electric field, and then it gives it to the conductor. The conductor gets that energy, and it becomes stored in the magnetic field, and then give the energy back and forth, the same thing here, back and forth, okay?